Why are negative weight edges not allowed in Dijkstra's algorithm? In the last two lectures, when we discussed about Dijkstra's algorithm, we kept mentioning that there should be no negative weight edges in your graph. That is, negative weight edges are not allowed if you want to apply Dijkstra's algorithm. Many of you would have thought, why is negative weight edge not allowed? What is the problem if you have a negative weight edge in the graph? This is what we are going to look in this lecture. So the core of this problem is that Dijkstra's algorithm is a greedy algorithm. What is a greedy algorithm? At every single stage, it will make the locally optimal choice. So what is the locally optimal choice in case of Dijkstra's algorithm? The locally optimal choice is that at any point among the vertices that you are aware of, whichever is having the shortest distance from the source, that is, whichever is the nearest vertex from the source, that vertex will be picked in this particular step. This is a greedy choice. And what is the core of any greedy algorithm? The core of any greedy algorithm is the greedy choice property. The greedy choice property says that whichever be your greedy choice that you are making, that greedy choice should ultimately give you the global optimum solution. And if this has to happen, this greedy choice that you make, this should hold. That is, at any later point, you should not have to revisit the choice that you made and change it. If that happens, the whole algorithm goes for a toss. So the core point is, whatever be the greedy choice that you make, that is the vertex that you're selecting as the nearest vertex present at this point, should hold whatever is its present shortest distance. That is, throughout the algorithm, shortest distance to this particular vertex should not change any further. This can change till the point you pick this vertex. Once you visit this vertex, it should never change in future. Why should it not change? Because how are you deciding the shortest path to other vertices? Let us say you have one vertex here A, then you have B. For now, consider that B is the nearest to A. So let us assume that you already picked B as the nearest one, and then you also checked the neighbors of B. And what will you do? You will update the weights of B's neighbors according to whatever is B's shortest distance from A. So this is how you will do updations in Dijkstra's algorithm. What will happen if you change the value of B later? All the updations that you made from B will also go invalid, because if you change the value of B at a later stage. So this is what will happen in case you have to alter your final decisions. Next thing, let us see how are these decisions getting altered. How is this distance to B getting altered when you have a negative weight? I will take example of a graph and I'll show you how it is getting altered. Okay, let us say this is your graph. This is the graph you're having. A, B, C and D. If this is your graph, what happens if you have a negative weight? Let us say this is having 1, 2, 2 and 3 as weights, and this particular edge, it has a negative weight. Let us say -2. What happens now? In the first step, you will choose A as the source vertex, which means distance to A is 0. And then you finalized the distance to A. This holds, well and good. What will you do next? You will see whichever are the neighbors of A. So you will pick B and C as the neighbors of A. And what will you do with B? You will update the distance to B as distance to A, which is 0, plus 1, which is the distance of edge AB. So final distance to B is 1. So what will you do? You will say final distance to B is 1. And what about C? You will do the same thing with C. That is, you will do 0, which is distance to A, plus the weight of edge AC, that is 2. This is the final weight of C. So you will say my final weight of C is, that is the shortest path to C, as of now is 2. So remember, at this point, you are not finalized with the shortest distance to B and C. As of now, you have only visited A. What is the next step? Next step, you are going to visit whichever is the nearest among these edges. So you know B is the nearest vertex at this point because the distance to B is 1, which means you will select B for the visit. At this point, whatever is the value of B, this is considered as final in Dijkstra's algorithm. So at this point, we are visiting B and we are saying 1 is the final shortest distance to B. What happens next? You will see the neighbors of B, which means you will see C and D as B's neighbors. And what happens now? Distance to C gets updated because BC edge is -2, which means distance to C will now become distance to B, which is 1, plus distance of edge BC, which is -2, which will make -1 as the final shortest distance to C. So distance to C will now get updated as -1. Till this point, it is well and good. Nothing worse happened. But the problem starts now. Let us say you updated to D also. That is not relevant here. We only want to know about B and C for now in order to show the problem. So this is where things get a U-turn. That is, if you visit C next, ideally, whatever be your shortest distance to B, that should never change because you already visited B and it is finalized. But what happens if you visit C now? When you visit C, you will get to know that B is a neighbor of C because there is an edge CB. And what is the distance to C? It is -1 according to what you already found. Plus, what is the distance of edge CB? It is -2. So which means your new distance to B becomes -3, which is smaller than what you already found. This means it violates greedy choice property because whatever you greedily picked as the shortest distance, that was 1, which got violated at a later stage because at a later stage you understood that you can reach B, which is at a distance of -3. And now you can think that what if you allow to visit B again? If you visit B again, what happens is it will say now distance to B is -3, which means I can update distance to C as -3 plus -2, which is -5. And if you keep doing this, you are never going to end. So you have to stick to the initial rule, that is you will visit only once and whenever you visit, it is finalized. But if you stick to that rule, the algorithm is not right because at a later stage, you have an option to correct it. And this should not happen in any greedy algorithm. That is what greedy choice property says. So the greedy choice property is violated here because you are not able to finalize the shortest path to any vertex at the point you are making the greedy choice. That is at the point you are visiting that vertex. And because of this, whenever there is a negative weight edge, your whole Dijkstra's algorithm goes for a toss and it won't give you the right shortest path. So what does that mean? If there are negative weights, you will not be able to find the shortest path at all from a single source vertex? No, that is not the case. The only point is you can't apply a greedy algorithm in this case. We already told in the previous lectures that whenever as a programmer you are approaching, greedy should be your first choice. But if greedy is not possible, then you should look for the alternatives, be it backtracking, be it dynamic programming. So coming to this particular problem, it so happens that using dynamic programming, you can actually solve this. Even if there are negative weights, using dynamic programming, you will be able to find the shortest path. There is something called as Bellman-Ford algorithm. Whenever we reach dynamic programming, we learn about it. So using dynamic programming, you can solve this problem with negative edge weights.